So mutual information is the amount, is the measure of amount of information about X we can have knowing Y. So it is kind of a correlation between X and Y. If X and Y are correlated with each other by knowing one, you know about Y. By knowing Y, you have something to tell about X. So that's like a correlation, similar to. Now let's take a look at this information. If Y is equal to X, then you can perfectly tell about Y knowing X. Or by knowing Y, you can perfectly tell about X. Let's see this is satisfied. Then if Y is equal to X, the conditional entropy X given Y is equal to 0 because there is no uncertainty left on X given Y because they are the same. Then mutual information is equal to HX. So that is the amount of information about Y one can tell by knowing X, or vice versa. So you perfectly know the other. So that's the amount of information. So self-mutual information in this case is just the entropy. So as this one says, knowing Y means knowing Y, X in exactly. The full information is obtained. Suppose now the other case, when Y and X are independent with each other. So these two random variables are independent random variables with each other. In such a case, the conditional entropy is equal to H of X. Why? Because X is independent of Y, conditioning with Y is just has no effect. So basically, in this case, hold on a sec. All right. So this one is the result that P of X given Y is equal to P of X for all X and Y's. In this case, basically, it come out that the entropy should be the same because by the definition, right? Basically, that one is P xy over all X and Y log of P X given Y, right? Take the negative sign outside. And then this one is nothing but right? And that can also be written as X. Right? So if this is true for all x and y, then basically that is the case. And then when we say that two random variables are independent with each other, that means this is holding. Or the other case, the two random variables are independent. We can say that the joint distribution is equal to product distribution, like that, for all xy's pairs. So by the definition of joint distribution, we can say this is equal to that, and if the two random variables are independent with each other, then that means this is true. Or in this case, the other case, basically py given x is equal to py for all x and y's. So by the definition, applying the definition, this is so. So we can have two definitions. Basically, if this equality holds, when this equality holds, we say that two random variables x and y's are independent with each other. Or if this is true, then we say that the two random variables x and y's are independent with each other. Okay. So that's the independence case. So suppose y and x independent, then this is true. Then by the definition of mutual information, one way is hx minus hx given y, but hx given y is equal to h of x. So mutual information is 0. So knowing y cannot tell anything about x. There is no correlation. There is no information. Okay. Now the case that when the x and y, when x and y are independent, we can easily show that the mutual information is equal to 0, as we have already shown that. But can you show the other way around? For example, if mutual information is 0, then the two random variable is independent. So that means xy independent only if mutual information is 0. Okay, so can we, yeah, so xy independent, so okay, so I think we have done that, right? xy independent, then mutual information is 0. That's the easy problem. Going this way, we have done that. Now I want to go the other way around. So that means if mutual information is 0, then x and y must be independent. That's what I want to show. But you can use the relative entropy which you have shown, then you can use that to prove this. So two distribution, mutual information is a relative distance. Here the relative distance of two distribution. The two distribution, the first one is joint distribution, and the second one is product distribution. Okay, and then we have proved in the relative entropy case the two distribution must be the same when the relative entropy is equal to 0. That means the joint distribution must be equal to product distribution. So that means X and Y independent. So I have proven already. Now this diagram shows the relationship between each measure that we have covered. So entropy of Hx is about the randomness of random variable x. H of y right here, and then in between there is a mutual information. And then h of x can be written as h of x given y plus mutual information. Or h of y can be written as mutual information plus h of y given x. And then here is the joint entropy. Joint entropy is a entropy of joint distribution. So it is addition of these two cases. So that's the relationship comes out right here. So mutual information between x and y, which is can be written this way or that way. And let's take a look at this one right here, h of entropy of x given y. That can be written as, using this equality right here, that one can be written as joint entropy minus h of x. So here is a minus sign here, so it is, this one is using another one, h of y plus h of x given y. Okay, so h of x given y is equal to h of x and y minus h of y. So using that one right here, we have h of y minus h of x and y. So the mutual information is addition of the two, and then basically entropy of, if you take away the joint entropy, this part only is left. So h of x and the h of y, if you add the two, this part has been counted twice. And the h of x and y is not counting this part twice, because it is h of x plus only this part, or h of y plus only this part. This part is not counted twice in joint entropy. So in order to find that part, you add the two and then subtract this, then you have this one left. So this is a useful diagram so that you can memorize this relationship.